Good morning. Welcome to the lecture series on digital electronics 18 EC 302C. And in today's lecture, we are going to learn how to simplify Boolean expressions. So, Boolean expression indicates specifies the output function of any digital circuit. Output of any digital circuit will be expressed as a Boolean expression. Means it will contain a number of variables and operations on those variables. So, a Boolean expression may contain any number of variables and any number of operations. So, then what is meant by simplification of Boolean expression? So, the simplification of Boolean expression means that reducing the number of variables or the number of operations that are present in the original Boolean expression. So, if a Boolean expression is given which specifies the output of a particular digital circuit or system, and if we can reduce the number of variables and the number of operations, so that we will get an equivalent expression which contains less number of variables and a less number of operations, then the circuit required to realize that expression is small, or we require only less number of logic gates to realize a function with less number of variables and less number of operations. So that is the importance of simplification of Boolean expression. So when after simplifying the Boolean expression, the circuit used to realize the simplified Boolean expression takes less cost or less components or less logic gates. So then how to simplify Boolean expressions? So Boolean expressions can be simplified by using already known theorems and rules of the Boolean algebra. So we have learned many of the theorems and the rules in the previous classes. So those rules and theorems can be used, or postulates can be used to simplify the given Boolean expression into less number of, so that it contains less number of operations and less number of variables. So first we'll review what are the various theorems or postulates that will be useful to simplify the Boolean expression. So here we have listed some of the theorems and postulates which we'll use to simplify the Boolean expression. So first we'll go through these theorems. Next we'll try to simplify some of the expressions so that we'll be familiar with how to simplify the Boolean expressions. So first thing here is related to the OR operation. OR operation. So when a particular variable is ORed with different elements, so then what is the result? So here when the variable a is ORed with 0, bit 0, logic low, then it will be same as the variable itself. And when a variable is ORed with 1, the result is 1 itself. That is a plus 1 equal to 1. And when a variable is ORed with itself, that is a plus a, it is equal to a itself, the variable itself. When a variable is ORed with its complement, it results in 1, that is a plus a bar results in 1. Next are the few theorems that are related to the AND function. So what happens when a variable is ANDed with either 0 or 1 or itself or its complement? So when a variable is ANDed with, or when a AND function is performed between the variable and 0, the result is 0. and when AND function is performed between the variable and 1, the result is a only, that is a dot 1 equal to a itself. When AND operation is performed between the variable and itself, then result is the variable itself. And when AND operation is performed between the variable and its complement, the result is 0. So that is a dot a bar equals 0. Similarly, by commutative laws, we have a plus b equals b plus a for OR operation, and by commutative law for AND operation, we have a dot b equals b dot a. And similarly, by distributive law, a dot b plus c equals ab plus ac. Similarly, a plus b dot c equals a dot c plus b dot c. And sometimes we can see some of the products a dot c in place of a dot c we have written ac itself. So the dot operation is sometimes ignored while writing. So here a dot c has similar meaning of that ac. So even though if dot is ignored, you have to think it as the AND operation between the variables. So similarly, by De Morgan's theorem that we discussed in the previous lecture, a plus b bar equals a bar dot b bar, that is complement of the sum of the variables equals product of the complements. Similarly, we have ab bar equals a bar plus b bar, that is complement of the product of variables equals the sum of the complements. And similarly, so one property of the complementation is when you take complement twice for any variable, it results in the same variable. That means a bar bar equals the variable a itself. That means when a complement is applied twice for a single variable, for any variable, it results in the same variable. So these are the basic theorems and postulates that we'll be using in simplifying the number of various expressions. So we'll take up a number of expressions and we'll try to simplify the expressions by using the theorems and postulates that we have shown here. So simplify the following Boolean expressions. So we'll take the first example. First expression is f equal to a bar b plus ab plus a bar b bar. And here you can see that the first two terms we observe, it is a bar b and it is ab, and here you can see that the b can be taken outside from these two terms, and what remains is a bar in the first term and plus a the second term, and the third term we'll write as a bar b bar. So why we are actually taking we have selected only these two terms, and why we have taken the b variable outside, that depends on what are the various theorems that we can apply. So here I thought that when b is taken outside, what is remaining is a bar plus a, and here I already know that a bar plus a equal to 1. So since this term, when I take b common, this term is coming, and which can be written equal to 1. So I have taken this b as common from these two terms. So this depends, and this will be known readily when you practice number of expressions for simplification. So, so the expression becomes this, and here you can see that it is b dot actually. So when there is no dot, when there is nothing, you can assume that it is a AND operation or dot. So this can be written as b dot, and from this theorem a plus a bar equals 1. So this is equals 1. So here it is written as 1 plus, we'll write the remaining term as it is, a bar plus b bar. And this I can write it as b dot 1, that is a dot 1 equal to a only. So that means any variable, AND operation is performed between any variable and 1 is the variable itself. AND operation is performed between any variable and 1 is the variable itself. That is b here, and the second term will be written as this. And next we will apply the distributive law. This is exactly b plus a bar dot b bar, and here we will apply distributive law so that our operation is distributed over, and so it can be written as b plus a bar and b plus b bar. So this is AND operation, our operation distributed over, and by distributive law it becomes b plus a bar dot b plus b bar, and this you can see that this b plus a bar in this test is, and you can see b plus b bar, our operation is performed between the variable and its complement is equal to 1. So this is b plus b bar equals 1, and here again you can apply this AND operation performed between variable and 1 equals the variable itself. So here this entire thing is treated as one variable. AND operation is performed between variable and 1 is variable itself, it is b plus a bar. Now you can see that the function got simplified to b plus a bar. So what is the original expression given for the function? It is a bar b plus ab plus a bar b bar. So overall it has two operations, two OR operations, a number of variables, number of products, first product, second product, third product, or I can say there are three terms and two operations. Now you can see that the simplified expression, there is only one operations, number of operations reduced by 1, and there are only two terms, b plus a bar. And now drawing a logic circuit or constructing a logic circuit for this expression will take less number of gates compared to constructing a logic circuit for the original expression. So when a logic circuit takes less number of logic gates, means it will cost less. So realizing the simplified expression is economical compared to realizing the unsimplified or original expression. So that is the advantage of simplifying the Boolean expressions, and this is how we can obtain this simplification of the given expression by using the already known theorems and postulates. So we look at more of the examples. So the example number 2. So here simplify the expression f equals a plus a dot b bar plus a bar dot b, and you can proceed in a number of ways how this can be simplified. So here you can see that from these two terms you can take a outside, or you can use the distributive law. Actually this is normal algebra will say that a is taken as common, but here this is actually a distributive law. By distributive law this can be written as a, actually written as a dot 1, right? So then when AND operation is distributed over R, you will get a dot 1 plus a dot b bar, and when you take the reverse case this becomes 1 plus b bar. So a dot 1 plus b bar. So when you distribute it becomes a dot 1 the first term, a dot b bar the second term. So this can be written as this way, and we'll write the remaining term as it is a bar b. And here we'll use the above theorems. Here you can see that R operation is performed between the variable and 1. So R operation performed between variable and 1 is equal to 1 itself. So this can be written as a dot 1 plus a bar b. And this can write it as it is a dot 1 is a itself, a plus a bar dot b. And this again you can apply the distributive law of R over, and that can be written as a plus a bar on top and a plus b. So here a plus a bar equals 1 and 1 dot a plus b. So this simply equals a plus b. So this is how we'll simplify the expressions. So now f equals this. So some less number of terms, less number of operations compared to the original expressions. Next we'll take one more example, number 3. So next we'll look at one more example, that is y equals a bar plus b and a plus b. And when this expression is to be simplified, you can see that there is nothing present between two variables. You can thought of as logical multiplication or AND operation. And here you can say this is or distributed over and and you can see that b dot, it can be written as by distributive law b dot a plus a bar, and this you can see that b dot, it is a plus a bar equals 1, so it is 1, and here b dot 1 is b itself. So the expression got simplified to single variable from the two variables and three operations. So this is how we will be using various theorems and laws that we know already to simplify the Boolean expression, so that realizing or constructing a circuit for the simplified expression takes a less number of gates and makes the circuit economical. So next we'll see some more examples of simplifying the Boolean expressions. We'll take one more example. Example number 4. Example number 4, we'll take up the example AB. Expression is, Boolean expression is AB plus AC bar plus A bar C AB plus C. So this is the expression that we need to simplify by applying the theorems. So it is A dot B plus it is A dot C whole bar, it is AC bar. For the total two variables there is a bar. It is A B bar C dot AB plus C. And then how to simplify this? So the same expression equals so it is AB and AC bar. Here we cannot take common, A cannot be taken in common because it is A bar, AC bar is a singleton, and so it is written as it is, and here is the AND operation, actually AND operation. So we will use the distributive law and distribute this AND over R. So then this becomes A B bar C dot AB plus A B bar C dot C. So this can be written as AB plus AC bar plus A B bar C dot AB and distributed over R dot AB plus A B bar C dot C. And here you can see that it is AB plus AC bar plus and here there is AND operation between all of them. So that means it can be written as A dot A dot b dot b bar dot c. The same expression, the same term can be written as, since there is an AND operation between all the variables, you can club the similar variables so that we can apply the theorems. So a dot a and b dot b bar dot c. And similarly, we can write here a b bar c dot c, and this simplified is ab ac bar plus, you can see that this a dot a equals a itself, and b dot b bar equals 0. B dot b bar is 0, and dot c. Dot c, and the remaining expression is a b bar c dot c is c itself, and here you can see that ab plus ac bar, and this term 0 dot AND operation between any variable and 0 is 0 itself. Yes, a b bar c. This equals ab plus, by De Morgan's, this can be written as a bar plus c bar, and this 0. If this entire thing is considered as variable, so our operation performed between this variable and 0 is the variable itself, so 0 can be ignored. This becomes plus a b bar c, and here you can see that what else you can do here. Here you can assume that a, by taking these two terms, that is r distributed over AND, there is an AND operation actually, so distribute over this r over this AND, so this becomes a plus a bar dot a bar b, a bar plus b, a bar dot a bar plus a bar plus b dot plus this. So here also we use distributive law, and over r over and, this becomes c bar plus c and c bar plus a b bar. And this can be written as a plus a bar equals 1, dot a bar plus b plus c bar. This is also 1 dot c bar plus a b bar, and here this 1 into something is something, so a bar plus b plus c bar plus ab bar. And this can be written as a bar by taking these two terms, again distribute a plus a bar dot a bar b bar plus b bar plus c bar is equals 1. This is a bar b bar plus b plus c bar. This you can write as again distribute b plus b bar dot b plus a bar plus c bar. This becomes, this is 1, so it is b plus a bar plus c bar. So this is how the expression simplifies to b plus a bar plus c bar. So next we will take one more example. We will be using De Morgan's theorem to simplify the expression. So example number 5, and the expression is a b bar plus a b c whole bar a b bar plus a b c whole bar plus a b plus a b bar whole bar. So this is the expression that we need to simplify. So how to simplify this expression? We'll do it step by step. So a b bar plus a b c whole bar kept as it is, plus what we'll do is we'll write this a as it is, and this b here it is distributed, so b plus a dot b plus b bar. and whole bar, and this you can see that AB bar plus ABC whole bar, and this becomes A, and this becomes 1 and this is AB, and again use the distributive law. AB plus this is A dot A, and there is a whole bar, and this you can see here again it can be written as AB bar plus ABC whole bar plus, here it can be written as, again use the distributive law, so this is A dot A is A itself, so when you take A by using distributive law, it becomes B plus 1, and there is a whole bar, and here you can see that next what we'll do means, here we'll apply for this term, we'll apply the De Morgan's. This becomes AB bar dot ABC bar, and just before going to this, what we'll do is, before applying De Morgan's, we'll simplify the term inside, so that is A and taken, it is B bar plus BC whole bar plus, here you can see that this B plus 1 is 1 plus 1 odd with something is 1 itself, so it is A dot 1, there is a whole bar, and here you can see that so inside this we'll again apply, so distributive law, and it is B bar plus B dot B bar plus C, so for this entire term there is a complement, and here it is A dot 1 is A itself, and there is a overall complement, and this you can see it is A dot B bar plus B is 1 itself, it is B bar plus C, there is a complement here plus A, and there is a overall complement, and here you can see that it is A dot 1 dot something is A itself, so A dot B bar plus C whole bar plus A, and there is a bar. So here you apply the De Morgan's. So here it becomes actually AB plus this one A So here, considering this as one term, considering this as second term, so there is a complement of sum of variables, and by using De Morgan's, the complement of sum of variables can be written as product of complements. It is equal to product of complement of first one. There is already complement there, so giving it one more complement cancels this complement, so it becomes a dot b bar plus c, or I can write complement of complement. Similarly, complement of this variable, it is becomes a bar. So now we can see here that it is double complement, so double complement cancels away, and it becomes a dot b bar plus c dot a bar. And here you can see, you can bring these two terms and you can write a dot a bar dot, so these two terms can be brought, and this is a dot a bar dot b bar plus c. And here you can see that this is a dot a bar is 0 dot b bar plus c. And you can see that when something is performed AND operation with 0, the result is 0. You can see that this entire expression got simplified to 0. So this is how we will use various theorems to simplify the Boolean expressions, so that will require less number of variables and less number of operations. So we'll look at a few more examples here. Example number 6. Example number 6. And here we'll simplify y equals ab plus c bar dot a plus b bar, a plus b whole bar plus c whole bar. So here, so in the first I will try to apply, we'll keep this term as it is, and here we'll apply De Morgan's, and this becomes a bar dot b bar plus c, and there is a whole bar, and this we can write it as and we can use the distributive law, and this can be written as a b dot a bar dot b bar plus a b c plus c dot a bar b bar plus c dot c bar. This is how we obtained is by distributing our operations over and this results in So here there is a dot a bar, so it becomes 0 plus abc plus here a bar, b bar, c bar. This c dot c bar is self is 0. So if you get a complement, put a complement here, and there is also a complement here. And here you can see what remains is abc plus a bar, b bar, c bar, l bar. So here you apply again the De Morgan's, and becomes abc whole bar plus a bar, b, sorry, here it is the AND operation, a bar, b bar, c bar whole bar. And this you can see that it is equal to, again apply the De Morgan's, then it becomes a bar plus b bar plus c bar and a plus b plus c. This is a simplified expression here for the original one. In this way we can try simplifying a number of expressions by using all the theorems and postulates that we defined earlier. So that makes to find various techniques to find the easy ways to simplify, or from which point to start and which theorems to use at which point. So all these things will be familiar when you simplify a number of expressions. And this is how we simplify the Boolean expressions to make the circuit less expensive, or to make the circuit economical to realize any given Boolean expression. And thank you.